Welcome to Physics Lab 2 on projectile motion. The purpose of this lab was to plot and analyze the projectile motion of an object over some period of time. This lab gave us a focus on two-dimensional motion, but mainly on how gravity affected our object, and physics principles are utilized to gain information on the motion of the object and to configure graphs in Excel and GoScript. At the conclusion of this lab, I was able to see similarities and differences between my observed and computational models based on their plots or graphs, such as drag and gravity, that curve having a lower curve than just the gravity curve itself. And we'll see why later. Fundamental principles and concepts. So Newton's second law and the momentum principle are equivalent, and equations that we used in this lab are final velocity, final position, the x form of the final position equation, and that net force is equal to change in momentum over change in time. Concepts used were that velocity is constant in the x direction for projectile motion, but velocity in the y direction is not, however, due to gravity. Important information. The system was a balled up piece of paper, and the surroundings was everything else around the paper. The initial position was at the origin for us, which we set that to a tracker. The initial velocity was 1.432 meters per second in the x and the y components, and the mass is negligible in this situation. A meter stick was used in our video to calibrate the measurements, as we usually do, and tracker gave us the ability to get motion data on the object as it moved through time. Here's a video of the motion. All right, so here's the coding for the gravity portion of the computational model, and we can see that we start off with our initial position and our initial velocity. Our initial position is 0 for the x, about 0 for the y, and 0 for the z component. And x and y component are 1.432 meters per second for the initial velocity and 0 for z. We start off with a time of t equals 0.167 seconds, and we step with the time of 0.036 seconds. And we stop at zero point 0.6 seconds. And until we get to zero point 0.6, the loop is going to run iteratively and calculate our position from the net force and from the velocity. And this is going to give us our projectile motion graph. And it's about the same for the drag force. The drag force coding is nearly identical, except that I created a second net force in which I included the drag force equation, which is the drag force coefficient b times the velocity squared times v hat. And I have the negative there to account for drag being in the opposite direction of the motion of the object. We have our models here, and we see with the position, y position versus time, we have parabolic motion, which is what we're supposed to get for the y, and we have a constant slope for the x, which is also what we're supposed to get for the x, because in x direction, we know that the velocity is going to be constant, and the velocity versus time for the x also shows that, as it has a zero slope, so the velocity is constant and not changing, but the y velocity versus time graph it does have a slope and it is changing, showing that there's a net force and acceleration. And here it's also similar for drag. There might be a little bit of error at the bottom left there with the velocity versus time graph. For the x position, we see above that the position versus time is constant. It's moving at a constant slope upwards. So that means the velocity versus time should also have a zero slope, like how we just saw in the previous slide, but it doesn't. So there may be some error there. But the y position versus time shows parabolic motion and a slope for the velocity versus time, which is correct because there's acceleration in the net force. Now here we have our observed model versus the computational model. The orange line you see is the observed parabolic motion for y, and we can see below it a light blue line and a light green line, a dark green line, I mean, and the light blue is the computational model of the y position for gravity, and the dark green is a computational model with gravity and drag. And we see that that's below the one for just gravity. And the reason that is because drag slows, not slows down, but decreases the amount of force that's being applied. Um, so it it makes the position go a less amount. So according to my velocity versus time graphs, the following paper doesn't exhibit terminal velocity anywhere because nowhere on the drag force velocity time graph does the slope go to zero, or rather it's constant. So a situation where terminal velocity could potentially be observed is if we drop the paper ball from a higher position and in a larger environment. And in terms of our if we threw the ball straight up with the same initial velocity, would it take longer or less or the same amount of time as with the parabolic motion? And to be honest, I'm not really sure. I tried to calculate this a multitude of ways, but I couldn't find it. So yeah, that's the end of this lab, and thank you.